Hello and welcome to this lecture. So, in this lecture we are going to look at how linear algebra and particularly symmetric matrices show up in another interesting area, which is from the area of statistics. So, when you have data and you have to look for relationships between them, correlations between them, things like covariance matrices are used, and that is from the statistical side. Now, statistics you may think is not directly connected to electronics, but that is not really true. In fact, a lot of electronic systems, elements, when you measure voltages and currents, they suffer from noise, and noise becomes a limiting factor in many situations. And to understand noise, you need to understand statistical probabilistic methods. Now, I don't want to talk too much about that in this lecture, so I'll keep it very simple, but still you will see how linear algebra and matrices enter the picture there, and it's also very, very important to understand that. Okay, so here is one very simple. So, one very important and simple statistical tool or method, so to speak, is something called a scatter plot. So, now the scatter plot will easily tell you if two sets of data that you collected have some relationship between them or not. Not maybe easily, but at least it will give you a picture from where you can figure it out. Here is an example of two data, some two pieces of data that let us say we have collected. This is height in meters of a person and weight in kilograms of the same person. So, for every person you are measuring height and weight. So, here is some various heights and various weights, and supposing I want to ask a question statistically speaking about this data, are height and weight related? So, generally speaking, you have a sense from the physical world that someone is taller is going to be heavier, right? So, they have more bone weight, they have more muscle maybe, whatever, more mass is there. So, if you are taller, then you're probably going to be, your weight is going to be higher. So that generally you may know, but here is data you have collected from some 10 people, and how do you infer that relationship? I mean, it seems to be okay, but how do you easily infer that? So what you can do is you can do a scatter plot. What is scatter plot? So basically you plot the two values in xy axis. In the x axis you have height, y axis you have weight, and you plot all these lines to points together. So once you see this plot, you sort of get a better feel for the how the data is behaving, how weight and height are correlated or related, right? Because it looks like, I mean, it's not an exact relationship, but as height increases, weight is also increasing. You can't write down a general equation for weight in terms of height as a simple formula and all, but because it goes sort of all over the place, it's a statistical data, it has variations, it's not exactly follow some formula, but nevertheless you can see that there is a certain pattern, there is a trend, there is a correlated trend you can observe. So weight increases as height increases. So this is a claim you can make, a principle that generally is true in some sense, but of course there may be some very small increase, or there may be even a particular case where when height was increasing, weight actually went down. It can also happen, right? So somebody can be short and very heavy, but somebody slightly taller can be lesser weight. That also may happen, but maybe it's rare, right? So that's the sort of claim that is being made with this kind of data. Okay, so scatter plots give you this, but you may also get a scatter plot like this. This is two other sets of data. I may not even care where the data came from, but if you look at this data, it seems like there's no obvious correlation. It's sort of all over the place, sort of spread out in all directions, and there's no way you can say when one is increasing, the other is decreasing or increasing, or there's no trend. I mean, it's all over the place. So how to, from the numbers, right? So just given the data, okay, if you plot, you see something, but then if you have a lot of data, or you have multi-dimensional data, right? So in 2 dimension you can plot like this. What if you have 100 dimensions? So today we deal with that kind of data all the time. So when you have 100 dimensions or 10 dimensions, how do you figure out this correlation, right? So for that we need to numerically infer something about the correlation. So given the data, numerically I have to calculate those with those numbers and then come up with some metric which will maybe go high when it's correlated, low when it's not correlated, so you can figure out something. So that's where these matrices and all that will enter the picture. Linear algebra will enter the picture. So let me show one possible way of doing it. So as we've seen before, correlation and inner product are sort of connected, right? So we're going to see how inner product can be used to derive some metric for this correlation. Okay, so here is data. What is data? So data, I'm thinking at this point as pairs. So I have two x1 and y1, two things I'm measuring from the same person or same object in some sense, right? So here For example, it could be height and weight. Xi is multiple observations of one variable, yi is multiple observations of another variable, and x1 and y1 are observations of the variable for the same state or same person or same thing, okay, same entity, okay. So likewise, I have observed n such values xi, yi. I have this data. Now, how do I think about the correlation between the xi's and the yi's? Okay, what I can do is I can think of the xi's together as a vector x. Okay, so this is where the linear algebra part slowly enters the picture, right? All the xi's together I am thinking of as a vector x. All the yi's together I am thinking of as a vector y. Okay, so now I know the inner product between x and y sort of tells you something about the correlation. When you do the inner product between x and y, it tells you what part of y is along x, right? And there is a precise way in which you can do it. So based on that, one can sort of define a normalized correlation between these vectors x and y, which I will denote as rxy, and you may want to measure this rxy as the inner product between x and y. So all these are real, by the way, right? So all these are real vectors. So inner product between x and y divided by norm x and norm y. So I'm going to normalize. So sort of x is getting normalized by norm x, y is getting normalized by norm y, so that the value of this this quantity will be somewhat under control, right? Otherwise, if x is very large, then inner product xy may become large. Y is very large, inner product of xy may become large, and you won't know much about the correlation there. The inner product may not play a big role. So we normalize x with norm x, normalize y with norm y, and think of this normalized correlation between x and y as represented by the inner product. Okay, so we go look at the direction along x, x by norm x, and then direction along y, y by norm y, and we take the inner product. I've pulled the norm x and norm y out of the inner product to make this look pretty standard. So now you can write down this norm in terms of the xi, yi. Inner product is just summation xi, yi, you know that. The norm is the square root of summation I xi squared, and the y for the square root of summation I yi squared. So this is one number which I'm going to claim tells me something about the correlation between x and y. Why is that? That's because of the Cauchy-Schwarz inequality. What do I know from the Cauchy-Schwarz inequality? That this rxy, right, what does Cauchy-Schwarz tell me? Absolute value of x comma y is less than norm x into norm y, right? That's what Cauchy-Schwarz is telling me. So by the Cauchy-Schwarz inequality, this rxy will lie between -1 and 1, okay. So the sort of claim is, if rxy is close to 0, x and y are orthogonal, they are in orthogonal direction, so maybe they are not that related to each other. On the other hand, if rxy is going to go close to 1 or -1, then y and x are linearly dependent, right? If it is 1 or -1, y and x are linearly dependent. So that's very, very strong correlation. They are along the same direction. So y may be some constant times x. So rxy is plus minus 1 if and only if y is plus minus cx. And what I have not said here, which I also said in words, is if rxy is close to 0, then x and y are sort of independent. They are in independent directions in that large space. So when n increases also, we can do something like so. So this kind of correlation measurement based on inner product is very, very popular in many areas. So anytime you have a lot of data like this, you want to figure out if there is some relationship, first thing you want to measure is correlation, and this is one type of normalized correlation you can do. So we'll also do something more. I'll talk about that in a little while. Okay. So here is let's go back to the two examples we had. Sure enough, it bears out the way we thought it should. The height weight data, which had this very nice looking correlation here, comes out with an rxy of 0.9865. This is really high. And this spread out data, where there was no obvious correlation, comes up with something like -0.17, which is close to 0. So you can see much higher correlation here, much lower correlation here. So already this metric is nice enough. But then we want to go towards larger dimensions, right? So every data point, instead of measuring only two variables x1, y1, maybe I want to measure multiple variables. So how do we go towards that? That's where the matrix idea comes in, okay? So whatever we did just now, instead of thinking of it as just one expression of the correlation coefficient, we can think of it in the matrix world. So here is the matrix interpretation to what we did, and you'll see this will result in something called a correlation matrix, which you may be surprised or may not be surprised. This will also end up being symmetric, okay? So you'll see how this comes about, okay? So let's see this. So here, once again, we start with this data, x1, y1 to xn, yn. I'm going to define a 2 by 2 correlation matrix, okay? So you'll see the correlation matrix has many of the elements that showed up in the correlation, normalized correlation, but except that they will show up in a matrix, and you'll see it'll be a little bit interesting, okay? So this is how I'm going to define my correlation matrix. I'm going to take this rxy is my notation for the correlation matrix. I'm going to take each observation I have, x1, y1, okay, think of it as a vector, right? I am going to, instead of, see, previously we thought x1, x2, xn as a vector, long vector. Now I am going to think of x1, y1 as a vector now. Put x1, y1 as a column vector and then multiply it on the right with the row vector x1, y1. So it is this vector and its vector transpose on the right side. So this will end up being a 2 by 2 matrix, right? I hope you see that. This is a column vector multiplied by a row vector on the right. This will be a 2 by 2 matrix. So likewise, I do that for every data point I have. I do it for x1, y1, I will do it for x2, y2, so on till I will do it for xn, yn, okay. And then I will average, I will just divide by n, okay. So this gives me a 2 by 2 matrix, and that I am going to call as a correlation matrix. So this sort of collects all the correlations that I can possibly have together in the data, okay. So this computes the correlation matrix. So now let me just go through this computation and see where I end up. So if you multiply, do the actual multiplication, you are going to get x1 squared, y1 squared on the diagonal and x1, y1 on the off diagonal element, right. So same thing you will get for every entry here, xn square, yn square, xn, yn. And now I have to add it up. So I see that my correlation matrix has this behavior, and it's very simple, right. So the diagonal elements are simply x1 square plus xn square, y1 square plus y1 square, yn square. So this is like norm x square and norm y squared, and the off diagonal elements is just the inner product, and these two are equal, right. So you notice here that these two are equal, and in particular this rxy is symmetric. So quite often when you have data like this, you can just go through and do this calculation and you will get a symmetric matrix. Now one of the problems with this computation is, if x1 by itself is very, very large, all the xi's are very large, and unnecessarily you will get very large numbers here, okay, and maybe that sort of confuses you a little bit, and sometimes it can really happen, data can be over a wide range, and then you may be misled by some numbers. So what people usually do is they sort of normalize these things, okay, and one important normalization is something with mean and variance, okay. So let's look at this mean and variance, which generally gives you a sense of how big the data is, how spread out the data is, okay. So mean of n numbers, which I will denote as x bar, okay. So notice we have been doing this bar for conjugate also, for complex, but here everything is real, so I hope there is no confusion. So I am going to define it as x bar, and it is defined as the average, right. So 1 by n into x1 plus xn. So mean is sort of like the center of the data, sort of one of those central metrics here, and if mean is very high, it means all the data values are very high. If mean is low, it means it could mean many things, but mean generally being high means the data values are going very high all over the place, etc. So this is an important metric to have. Another very interesting metric is something called the variance, okay. So a variance of x1 to xn, which I will denote as sigma x squared, is basically defined as in this fashion, okay. So it's again an average, but what you average is x1 minus x bar whole square, xn minus x bar whole square. So if mean is the center, variance measures the spread of the data, how far away I am from x bar each of my elements are, okay. So you may have mean being some value x bar, and for instance one case may be all the x1 to xn are equal to x bar, okay, everything is x bar. That could be one way in which you get x bar, right. But then there the variance will be 0. But you can also say that if x bar is the mean, but the values are on opposite sides all the time, right. So one value very high negative, left side of x bar, right side of x bar, on average you will get x bar, okay. So a lot of values like that. But if that is the case, then the variance will be high, because you look at what you are doing x1 minus x bar. So how far you are from the mean, and then you are squaring it all up, okay. Whether it is positive side or negative side, it will be increasing, that is why you are squaring it, and then you are dividing by 1 by n to get the sigma x squared. So this gives you the spread of the data. So mean and variance are a very important part of any data analysis. So whenever you have a bunch of data, you want to compute mean variance, see how much the spread is, see how much the where is the center, etc. Okay, here are a couple of derivations. I am not going to go through the proof of this. I will urge you to do it. It's an interesting and important proof. So you can check that sigma x squared, while written like this, if you simplify, this will be exactly equal to this. It's 1 by n x1 squared plus xn squared minus x bar squared, okay. So you can see why there's another term, middle term here, it will sort of end up cancelling or becoming something with the second term. It will combine with the second term and it will give you this, okay. So this is sigma x squared. There's also a related definition, it's called the standard deviation. It's a square root of this guy, okay. So it's sigma x, okay. I just want to warn you, some people use n minus 1 instead of n for the normalization. It doesn't change things too much when n is very large. We will keep using n in this course at least, okay. So this is mean and variance. So mean and variance are very important. So here's a quick example for my height weight data. If you look at the mean of the height, it ends up being 1.662. The mean of the weight is 66.8 kilograms. The variance of height is some number. Standard deviation, notice standard deviation 0.096 meters. So it means 1.6692. The standard deviation is about 0.1. So you're not deviating too much. It's about 0.1 about the height. The weight on the other hand is as a variance of around 225. Standard deviation is 15. So standard deviation is a nice number to look at, right? Because it's in the same units as the original data that you have. And you can see 66 plus 15, 66 minus 15. So the data is sort of around that, right? Give or take a few, right? Maybe you can see the 93 is a little bit off, maybe 1 or 2 standard deviations on either side, and you seem to be getting all the data within that. So standard deviation is a good measure of the spread. Mean is sort of the measure of where the center of the data is. So this is just a quick example. Okay. So now we're ready to move one step ahead and define something called the correlation coefficient. Now this is going to sort of centralize the data and then normalize with the mean, with the variance, so that you get a very good measure of the correlation. Okay. So once again we start with data. Again we are only in 2 dimensions, just 2-dimensional data we are looking at, and we compute the means as before, as defined before, and then we'll centralize the data. So notice what happens when I centralize. I take each xi, subtract the x bar from it. I keep only how it deviates from the mean as my data. Similarly, from each yi, I will subtract the y bar. Okay, I will keep only how I deviate from my mean as the data. Okay, so this is called centralizing the data. What happens is, if you take the mean of the centralized data, you will get 0. Okay, see if you add up all these x1 minus xn divided by n, you will see that you will get 0. Check that again. So the mean of centralized data is 0. So from mean being x bar, you went to mean 0 by centralizing. Mean is x bar, y bar originally. You subtract x bar, y bar from each guy, you go to mean 0. So this is a good way of centralizing and then defining correlation. Okay. So now correlation coefficient between x and y, which I will denote as rho xy, I am going to define exactly like before, except now I am going to use my variance and terminology of mean and all that. So instead of computing the inner product with the non-centralized data, we will compute the inner product with the centralized data. Okay, so this is the big difference in the correlation coefficient definition. Of course, you have to do a 1 by n to make sure things work out. And then in the denominator, I am going to divide by sigma x, sigma y. Okay, so if you notice, sigma x, sigma y is basically nothing but the norm of these vectors in some sense, right? So that's what you get here. So if you simplify this using the formulae before, you will see that the numerator is simply the inner product between xi minus x bar, y minus y bar, and then the denominator is the norm of xi minus x bar, and this side is yi minus y bar now. Okay, so this is a correlation coefficient. Here I've brought in the mean to centralize the data, and it's a much more standard definition. Now again, anyway, since it's anyway inner product by norm into norm, Cauchy-Schwarz still applies, right? Cauchy-Schwarz tells you that rho xy is between minus 1 and 1, and if rho xy is 0, then maybe this x minus x bar, y minus y bar are orthogonal to each other, not very related. But then if rho xy is close to 1 or minus 1, then there is a very clear relationship between y and x. Okay, so this is correlation coefficient. Now we still have not got matrix. We're going to get the matrix next. So now just like we defined the correlation matrix, you can also define a covariance matrix. We'll do that first in 2 dimensions, and then we'll go to a larger dimension. Okay, so here is the data x1, y1 to xn, yn. Centralized data is also there. Now the covariance matrix is the correlation matrix of the centralized data, right? So we had a correlation matrix before. Instead of defining the correlation on the basic data, you define the correlation matrix on the centralized data, you get the covariance matrix. Okay, so here is how it goes. You remember the CXY, I'll denote it as CXY, the covariance matrix, instead of RXY. So with this data, I simply use the definition of RXY again, right? So you see the diagonal elements are the norms of the vectors, and the off diagonal elements are the inner products between the 2 vectors, and then I do a 1 by n. Okay, so this is the thing. So you notice very easily that Cxy is nothing but the variance on the diagonal, sigma x square, sigma y squared, and on the off diagonal you have rho xy times sigma x, sigma y, rho xy, sigma x, sigma y. Okay, so this is nice and normalized, and you see the whole thing working out. In particular, Cxy ends up being a symmetric matrix. Okay, so one can extend this to m dimensions also. So here is the m dimensional extension. So far we have looked at only 2-dimensional data, right? Each data point is only x1, y1. We measured only 2 variables. Now I'm going to measure m variables. So here is this notational difference here. The first data point I'm going to call as u1. This is now a vector itself, m dimensional data, so it's got m variables. Okay, so every measurement I'm making is m variables. Maybe you can think of height, weight, what else about a human being, various dimensions, length of the hand, length of the leg, so many different dimensions you can add, right? When you go to a tailoring shop, the guy is measuring you maybe all the measurements, shirt size, pant size, everything, right? So you can put all those things together, you will get a big vector which sort of captures the person. So now we can think of the weight as a function of all those things. Is this related to that? Is arm length related to leg length? You can ask all sorts of questions like that and then work it out, but we are not looking at that data. But let's think of this as like that, right? So u1 is u11 to u1m, u2 is u21 to u2m, un is un1 to unm. How am I going to define covariances? First I have to define a mean vector. Okay, mean vector I'm going to call as u bar, then u bar 1 to u bar m. Each of these things are basically, I take each vector, add up all the vectors and divide by n. So I'll get a vector, right? So that is the vector u1 bar to u1 bar. So u1 bar is the mean of u11, u21 all the way to un1, like that. Again, second one u bar 2 is the mean of the second coordinate, second variable, etc., etc. Okay. So once you have the mean, you can also define variances, right? So what are variances? The ith variance, sigma I squared, is basically variance of the ith coordinates. You take the ith variable in each data, right, in each data vector, collect all of that together, find the variance of that. I'm going to call it as sigma I squared. Now there are m vectors and I can do all possible covariances, right? I mean correlations, okay? So that is what I'm going to call as rho ij. Rho ij is what? Correlation coefficient between ui1 uin and uj1 ujn and I not equal to j, let's say, right? Previously we had only two vectors xi and yi, x and y, right? So you could do one correlation between them. Now if you have m of them, I can pick any I and any j, ask for the correlation between them, right? So I can do that. That is called rho ij. And sigma I square likewise is the variance. So now I have mean, I have variance, I have correlation coefficient. I can start defining my covariance matrix. The covariance matrix, which I am going to denote as Cu, okay, is going to be same as before, 1 by n. This centralized vector u1 minus u bar, think of it as a column vector, right? So this is a column vector, and then this is u1 minus u bar, which is a row vector, okay? So every element, every factor here, every term here is a column vector multiplied by a row vector, column vector of length m, row vector of length m. So it will be a m cross m matrix. You add several of these m cross m matrices, you will get an overall m by m matrix, and I will divide by 1 by n, and that is my covariance matrix. Now this, if you simplify, okay, carefully, I am not doing that simplification, I will leave it as an exercise to you. If you simplify, you will get this. Okay, so what is my covariance matrix? All these variances will appear on the diagonal, sigma 1 squared, sigma 2 squared, sigma m squared, right? So if you see here, all the diagonal elements will be just the same element squared. So you add them all up, divide by 1 by n, you will get the variances of the centralized data. Okay, so I have made one mistake here. So if you do this very carefully, you notice that the diagonals are all the variances, and if you look at the off diagonals, you will get the rho ij multiplied by sigma I sigma j. Okay, so if you look at the 1 comma 2th entry, it's going to be u1 minus u bar 1 multiplied by u1 minus I'm sorry, u11 minus u bar 1 multiplied by u12 minus u bar, and then like u bar 2 and all that, right? So it will be the 1 comma 2th element, and that will give you the rho 1 2 times sigma 1 sigma 2. So I have not provided all the details here. You can try and check it up, go back and look at the 2 by 2 definition where we saw all the working out. So you will see it will work out exactly like that, and you will get on the diagonal elements, you will get sigma 1 squared to sigma m squared, and the off diagonal elements will be rho ij times sigma I sigma j. Okay, so this is the covariance matrix that you will get, and you can observe as usual that this is a symmetric matrix. Now this covariance matrix that we have defined using any m dimensional data has many more powerful properties, and that we will see in the next module. Thank you.